start recording. So before we go on to our next topic, which is thermoplastics and well, actually plastics. So we're going to start with sort of a little bit of a review from 321 on introduction. Are there any questions, both from the room and also on Teams? Okay. Oh, that's interesting. Okay, so I'm going to go ahead and share my screen. And since I now know I can see the chat, if I'm not stupid, we'll go ahead and get started. Okay. Well, I believe that most of you probably do remember some about plastics and polymer-based materials from 321. I always think that when we start moving to processing of plastics, we do a little bit of a review, and my clicker doesn't work. So we want to just kind of talk about polymer-based materials. So when we talk about plastics, and a lot of times when we say plastics, we refer to thermoplastics, and then we also may say thermosets or thermosetting plastics. We can also call these polymer-based materials. And I think in 321, we often really looked at the polymer itself. So these are materials, whether they're thermoplastics or thermosets, they're made up of polymers. So these are those very, very large molecules made up of many repeating units. And so most of the time we may have the word poly in there, polyethylene, polypropylene, polycarbonate. We also have polyurethane, polystyrene, and a few others. And so we want to kind of look at the characteristics of these materials, but more from the processing point of view, not as much the mechanical properties. So we recognize that polymers are going to be made by a chemical reaction, and we refer to this chemical reaction as polymerization. And now we kind of say, well, you start with the monitors and then you kind of create these, depending on what we're doing. But when we form the actual molecules or we form the final molecule, that is what we refer to as polymerization. Okay, and now, so one of the things that we'll review and talk about is, does polymerization happen during shaping or processing? Or does polymerization happen like at the chemical company and we're not doing any chemical reaction when we shape the material? If you're thinking, if you remember that doing a chemical reaction during processing makes it a little more complex and complicated, that is correct. So it's easier if we don't have to do the chemical reaction. And the other thing I think we should be kind of aware of, and why in some cases, like depending on the setting, sometimes plastic refers to, and the most official definition I've heard is that a plastic is a polymer-based material that contains additives. Almost all plastic materials are polymers and something else. So those something else could be dyes and colorants. Oops. There we go. So polymers are actually kind of boring colors. They're either transparent, kind of a dull white, or if we have some, in some cases, kind of like a ugly yellow brown. We think of plastics as pretty materials. We think of plastics as materials where we don't have to paint. And that's because we add colorants and dyes to the material itself. We also are likely to see fillers, plasticizer, and a few others. So some materials have a certain amount of polymer, and then we add a lower cost material to just take up space. We might have talked about a plasticizer in 321 that lowers the glass transition temperature. And so we can have the material be more flexible. An example of that is rigid PVC pipe versus vinyl. We also may add anti-static, anti-flame, anti-smoke, and a few other things could go in there as well. So again, most of the time we do talk about the polymer itself and how the polymer behaves, because that's what controls the properties the most. I don't even know why I bother with my little gadget. Because every so often it works. Okay, so let's review thermoset and thermoplastic. And we're going to start with thermoset because we're going to talk about that in the least. So in a thermoset, if you kind of remember from 321, a thermoset is a material that does not flow when heated. So once a thermoset is formed, it's pretty much solid. It's going to hold its shape. Eventually, it will burn or char. And so most of our thermosets, epoxy is a thermoset, Bakelite is a thermoset, some of our polyurethanes are thermosets as well. So once you have that polymer formed, you can heat it all you want, it's not going to flow. Eventually, it will burn or char. So what does that mean? That means that polymerization, and oftentimes it's our final polymerization, is done when shaping. So when we shape a thermoset, we actually have to do a chemical reaction. If we're interested in remembering, thermosets are either very heavily cross-linked, or they're three-dimensional, or the molecules are sort of three-dimensional covalent bonds. Most of what we refer to as plastics are thermoplastics. And so thermoplastics, these will flow when heated. We also see that there is no chemical reaction during shaping. And this is often what we refer to when we say plastic. If we say this is made out of plastic, we're usually referring to a thermoplastic. Anywhere between 70 and 80% of the polymer-based materials that are processed are thermoplastics. And so let's sort of, again, remind ourselves on the structure of thermoplastics, and again, what we're actually doing when we process them. Okay, so if you remember, when we talk about polymers, when we talk about the long molecules or the chains, we're referring to how that repeat unit is arranged. So we can have a repeat unit. So if I kind of have my repeat unit identified by a circle, and then I get even lazier and I just have it as a line, we can talk about a linear polymer. So they're going to be just sort of stretched out. These are still three-dimensional molecules, and they're covalently bonded. So there is a three-dimensional geometry. There may be some twists in there as well. They're either going to be linear or branched, where we do have branches that kind of come off the main polymer. So that means that the actual properties are these van der Waals bonds or forces. I say bonds. In materials, we say bonds. My chemistry friends often say forces. So if you remember, these van der Waals bonds or forces are the positive portion of a molecule being attracted to the negative portion of a molecule, either the same molecule or a different molecule. They are very dependent on distance, as the distance between the molecules increases, the strength goes down, and it is to the third or fourth power of the distance. So the closer the molecules are together, the higher the strength of these bonds, therefore higher strength, higher modulus, oftentimes lower ductility, and some of the other properties that go with it. Okay, and so when we kind of melt or process or deform the plastics, what we're doing is we're interfering with those van der Waals bonds. We're allowing these molecules to slide, change shape, and then we're allowing those bonds to reform again. The most common way in which we lower the strength of those van der Waals bonds is by increasing the distance between the molecules. And the easiest way to do that is to increase the temperature. So what we're doing is increase the temperature, those molecules, the distance between the molecules increases, strength goes down, those molecules can flow, change shape, and then everything, once it cools down, the molecules get closer together and the van der Waals bonds get strong. Okay, so that's kind of the general idea of what we have going on. So whenever we're sort of thinking about thermoplastics, I like to visualize these large molecules moving relative to each other. That's somewhat different than in a metal. What's moving relative to each other in a metal? Will, sitting in class, what do you think, Will? When it's liquid. Anyone want to? It's actually individual atoms. Yeah. And how about when water flows? What's the size of, what's moving relative to each other when liquid water is moving? And how many atoms are in those molecules? 3, right. So when a metal flows, we have individual atoms moving relative to each other. When water flows, we have a molecule that has 3 atoms. Remember our polymer molecules, these could easily have thousands of atoms in the molecule. So just kind of think, so when we think about how these flow, and we talk about the viscosity, they don't really, this material does not flow like water or liquid metal will flow. It's much, it's a much slower process. Okay, and again, I kind of imagine like these very long, large molecules having to flow. Now, again, as I said, the properties are really dependent on these van der Waals, and we also kind of can remember that these are low strength compared to the metallic bonds. And that's why all the properties of thermoplastics are low compared to that of metals. Yes. Okay, so let's kind of move back to processing. So oftentimes our thermoplastic material, it's polymerized at the main company, and it's oftentimes sold in granular form. This one looks more spherical on the left. On the right, it looks more like they've been chopped up into little blocks. So this oftentimes is what our starting material is going to look like, and then it becomes the part. And so what we're doing is when we're processing it, we're going to be heating this up, going to allow all of these molecules to flow and form the shape, and then the van der Waals bonds get stronger. What we see over here is this particular material kind of has a nice clear, and here we have some little green pellets that we add, and then here are some yellow ones. So oftentimes when we're processing a colorful material, we have just a small amount of polymer that has a pretty rich or intense color, and we mix that with something that's either clear or white to get the actual material. So that way, it makes material handling a little bit easier. In lab next week, we're going to be doing surface roughness. I also will pull some of my parts out, and I have a part that was made out of this clear green mix, and you can sort of see what kind of color we would get from that kind of mixture. But again, we have to add the color to the material. Okay, this is one of, I always like talking about the arrangement of polymer chains. I've recently talked with a 3-year-old, and she oftentimes sketches the amorphous arrangement of a polymer chain. So polymers can either be amorphous or semi-crystalline. So if we have a crystalline region, we know that we go with the folded chain model. So those chains or molecules of polymer arrange themselves in this folded chain. We see that this distance between the chains generally is smaller than if we are just having a random arrangement. We also have the amorphous. So an amorphous region or an amorphous polymer, we just have the polymer chains are sort of just randomly arranged, which is why oftentimes 3-year-olds draw that very well. So again, the distance between the polymer chains in amorphous is generally larger, and that leads to lower bond strength, lower strength, higher ductility, and so forth. So if we are semi-crystalline, we have regions of both. So we would have some of our chain stacking, and then we've got some amorphous, and then we have some of our chain stacking as well. And we know that the semi-crystalline will have some regions or properties of both the amorphous and the crystalline. Now, let's kind of think about this from a processing point of view. When a crystalline region melts, so remember, melting in that classic definition is long range order to short range order. So we go from something that is crystalline to something that is not. And so when a crystalline region melts, it's going to lose its long range order and go to short range order. What tends to happen to the density of a material when we go from crystalline to more of a liquid, or from long range order to short range order? Anyone? What happened in our liquid metal? Excuse me, what happened in our metal when we go from solid metal, which is crystalline, to liquid metal? What, or the other way, what happens in our solidification of our metals at the location of the last liquid to freeze? Oh, somebody, there's a chat. Did someone answer my question in the chat? Oh my God, if I can get my cursor over here. Let's see, do I have an answer in the chat, or is someone telling me you can't hear me? Oh, very good. So Jacob says it expands. Very good. So thank you, Jacob. So when we go from crystalline to melting, it expands. That means that when we go from liquid to crystalline on forming, it contracts, and we call that shrinkage. So that means the more crystalline our material, the more shrinkage we're going to have. Okay. So I'm going to try to advance. I don't know why sometimes my PowerPoint is not happy with advancing. Let's see if this, there we go. I have no idea why. Okay, so again, and I think, I can't remember if I asked that on the reading assignment, but your book does talk about how a crystalline material will tend to shrink more. So processing, as we process a material that has a higher degree of crystallinity, it actually is a little more difficult because we can get some more shrinkage. So we want to kind of look at the processing and our important temperatures. And let's start with the amorphous. So the amorphous doesn't really have a phase change. So we really don't have a significant arrangement change. We do have a glass transition temperature. And again, to remind ourselves, if we're looking at density versus temperature, and we know that the density goes down as the temperature increases, we do see a point where the slope of the line changes. That's the glass transition temperature. We can also sort of think in terms of properties that our vinyl shower curtain is sort of an example of a material that is above the glass transition temperature. Rigid PVC pipe is an example of below, just to, again, kind of give us some review of that material. Again, we also see that we may have a large drop in modulus or stiffness above the glass transition temperature. So we can kind of look at here where we see, if we look at stiffness versus temperature, we also see a large drop in stiffness at the glass transition temperature. And then we also have what we call a processing temperature is the softening temperature. And above the softening temperature, we would classify the material as a melt, which means it can actually flow on its own in a reasonable amount of time. So when we are, for instance, shaping a material, we oftentimes are going above the softening temperature. Okay, so again, just what these temperatures are. Now, again, as we just chatted about, our crystalline region will have a melting temperature. And so we know that a melting temperature, we have that distinct change in density at a specific temperature. And as we just described, for a crystalline region, we can have shrinkage. So when we go from that short range order to long range order, we do tend to see a contraction, and then we get shrinkage. Now, we are used to, and we talk about a melting temperature. Plastics generally have a temperature range. A plastic is not, the size of the molecules within a plastic are not uniform. So we often talk about a range in which the materials are going to melt. That doesn't mean we still show a melting temperature as a distinct temperature on our graph, but it's usually a range. And if you look up plastics, you'll see a range for melting. We generally are going to process or shape above the melting temperature. And the melting temperature is going to be higher than the glass transition temperature. So here we have the density versus temperature plot from our 321 textbook. So we see crystalline, we see our glass, and then our semi-crystalline, we see this change in slope at glass transition temperature, and then this distinct large change in density at the melting temperature. And then again, we can also look at what happens to the stiffness above the melting temperature. The stiffness of the material drastically decreases. Same with above the softening temperature for amorphous. Okay, I know you oftentimes think about viscosity, and this is sort of a picture. This is a picture of a melt of plastic, and we sometimes refer to the plastic when it can easily flow as a melt that's coming out. So if this was water or metal, it would not. We wouldn't be able to see that droplet. Viscosities for polymer melts, they're going to be high, 10 to 100. And then whereas molasses is 5 and water is 0.001. So again, I think from your, in fluids, did you deal with any high viscosity of materials in fluids, or was it mainly lower viscosity? Lower, yeah. What, mainly water and air? Yeah, right. Yeah. So we also can kind of talk about how these are non-Newtonian as well. What we do need to recognize is our viscosity increases, meaning it's going to, the flow characteristics are going to get even slower when we have longer molecules. So the higher the molecular weight, the higher the viscosity, and then lower temperatures. And again, how this might influence processing. Polymers also are kind of interesting. And we really aren't going to go into this in detail at all. I just think we need to realize that polymers, plastics are very complex. And oftentimes we try to really simplify it, but there are some kind of modeling issues with that. So Newtonian fluids, the viscosity is independent of the shear strain rate. But with polymers, we have this concept called shear thinning. And in that case, what we have is that the viscosity goes down as the shear strain rate increases. And that's unusual. What that means is that if we have high shear strain rates, and we may see that in thin gates, that we oftentimes the material is going to flow better than we would expect it. And here just is where we can see that the viscosity is going to decrease as the temperature increases. We also see that it decreases as the shear strain rate increases. So this is again going to be different than our, I want to say our typical, but our Newtonian fluids. I think this is kind of fascinating. And I think you should be aware of the term and what it means, and that most polymers or plastics do experience this shear thinning. But we're really kind of looking at this from an overview and a general point of view. Now, we love numbers or properties that tell us, hey, how does this work? Is this good? And so the melt flow index is something that we often may see on a MatWeb or another site. So here we have this is a particular type of low density polyethylene. So low density polyethylene is number 4 on the recycling. So you may see some bags made out of it. And so here we have the melt flow index. It references an ASTM spec, and we see that it is 5 grams per 10 minutes. So it's just a number that tells us or is related to the viscosity. So it is, for a prescribed temperature, the mass that flows through an opening in 10 minutes. So again, it really kind of, it is related to the inverse of viscosity, and the higher the value, the easier the flow. And so you might talk about a material that has a high melt flow index. That just means it's going to flow easier. It will flow faster. There are certainly some issues with the melt flow index that does not necessarily duplicate what's in that happens in the mold, but this is a very common way to describe a polymer melt. The melt flow will change, so we want to kind of, you know, consider that the size and size distribution of the polymer chains will change the melt flow index. So this is something where from one manufacturer to another, you may have the same type of polymer, but these may flow differently because the size and size distribution is going to be different. Okay, we're almost done with the kind of the background. I always get kind of excited by this. The more I talk about plastics and polymers, the more fascinated I am with them. I used to think that polymers were not very exciting compared to metals, but now I'm kind of changing my tune on that a little bit. Okay, so again, if we kind of finish off with looking at those aspects of the material that affect processing. And so we want to kind of look at cooling rate. So if we kind of think about it, slower cooling allows for more a higher degree of crystallinity. So slower cooling allows for a higher degree of crystallinity. Okay. And again, whether we want that or not will kind of depend. Higher degree of crystallinity gives us higher strength, but we also may have a little more shrinkage as well. And let's kind of think about how much shrinkage we get. If we have an amorphous plastic, we're talking about 1.5% volume shrinkage. If we are semi-crystalline, we're looking for up to 7%. And we have, note, again, this is going to make sense, a larger shrinkage for higher crystallinity. Which means that the cooling rate actually does or can influence the shrinkage. We don't necessarily see that with metals. Well, our final thing that we want to look at, and I think in the reading assignment, you did, I did ask for you to compare thermal conductivity and maybe specific heat of metals and plastics. But let's look at, again, some of our differences between plastics and metals. we tend to do a lot of processing more of metals, and so we can kind of compare plastics and sort of see how that's different. So plastics have a higher specific heat. So we're looking at 2 to 4 times higher, but their thermal conductivity is very low. So our thermal conductivity is 400 to 800 times lower. So while plastics have a lower melting temperature, we heat a plastic, or we take a plastic to a much lower temperature than we do a metal. We do see that because plastics are not good thermal conductors, a thicker plastic is going to take, it's going to take longer to cool than if we had, a metal going through that same temperature difference and thickness. So again, we sometimes think about, oh, plastics are low temperature. Yes, they are, but they also, from a thermal point of view, the thermal conductivity is not good. So for a thick plastic to cool, that takes longer because you don't have as much mold wall. Okay, so we also have this kind of interesting concept in terms of the density of the polymer. And your book calls this compressibility. And so what we're looking at is, and this is related to the molecules. So the fact that those polymer molecules can align and get closer, meaning that we can have some changes in density due to pressure. Well, that also means that we might have some both compression, but also expansion. Now, the basic statement that we will care about is that we can actually have residual stresses from pressure gradients. We often think about residual stresses arising from temperature gradients. And in metals, most of our residual stresses come from temperature gradients and differences in thermal expansion contraction. For polymers, we often see it's more pressure gradient. So again, our book kind of talks about that a little bit. I really think that as long as we just recognize that residual stresses can come from pressure gradients, the book does kind of have a nice little explanation of this. Okay, and the last that we've talked about is plastics have a lower value of melting temperature and not a specific value. So we're really looking at plastics melting and also therefore freezing, not at specific temperatures, although we love to talk about that. Okay, so this I hope, again, so as we move into our processes, we want to kind of have this in mind as we look at our different processes. Okay. Okay. What time is it? 9:39. Okay. So we're going to talk about a few different processes. The first one that we're going to look at is injection molding Injection molding is one of the more common processes. Most plastics, I wouldn't say most, many plastics are produced by injection molding. And so we oftentimes see injection molding of thermoplastics and then alternative processes to injection molding. Injection molding, we get some of our more kind of common, again, processes. I think in our textbook kind of says, well, injection molding is kind of like similar to die casting, in that our basic process is to feed the thermoplastic into a clamped die under pressure. And then when the mold opens, the part is ejected. Okay. I think it might be kind of fun before we go into talking about all the, kind of going into the slides. Let's see if I can get my little video clip that I have of injection molding going. So let's see how this goes.
To better understand the injection molding process requires understanding some properties inherent in plastic itself. The simplest definition of a plastic is any natural or synthetic polymer that has a high molecular weight. There are two types of plastics, thermoplastic and thermosets. Thermoplastics undergo a reversible change from solid to liquid when heated, and can be cooled and reground for reuse over and over again. Thermosets undergo a chemical reaction between two reagents when heated and achieve their strength through the interlocking chemical bonds. Once molded, thermosets cannot be resoftened. While thermosets are injection moldable, most materials used in injection molding machines are thermoplastics. Injection molding plastics is extremely complicated because of the infinitely changing pressure, temperature, and velocity inside the mold. These molding conditions directly affect the properties of each molded part. A change in any of the conditions will alter the parts produced. There are four primary elements that influence the plastic injection molding process: the molder, the material, the injection machine, and the mold. There are a variety of injection molding machines in use today. The vast majority of these machines are hydraulically actuated and have 3 platens. But newer styles, such as 2-platen injection molding machines and electric injection molding machines, are now gaining market acceptance. Injection molding machines range in size and complexity from desk-size units up to machines the size of a small house. Most injection molding machines are horizontally oriented, but vertically oriented molding machines are available. These vertical machines are primarily used for insert molding. All injection molding machines are a combination of 2 systems, an injection system and a clamping system. The injection system heats the thermoplastic material to its appropriate viscosity or flowability and then forcefully injects it into the mold. There are 2 types of injection mechanisms: the reciprocating screw, which is the most common, and the 2-stage screw. The main parts of the reciprocating screw injection system are the hopper, a reciprocating screw inside an externally heated injection barrel, a hydraulic motor, and an injection cylinder. Resin material is fed to the injection barrel from the hopper. These hoppers may be filled manually or vacuum-fed automatically, and often have dryers attached to the top to remove the moisture from the material. As the resin enters the injection barrel, it is driven forward by the rotation of the screw, which is powered by the hydraulic motor. The resin plasticizes or melts as the turning screw drags it towards the nozzle end. This is referred to as drag flow. Drag flow causes the polymer molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the injection barrel. The heating bands bring the material to its final temperature and compensate for the radiation heat loss. The temperature is controlled by 3 thermocouples in the barrel and 1 in the nozzle. Over time, many different mold designs have been developed that meet specific injection molding requirements. These mold designs include the Cold Runner 2-plate mold, the Cold Runner 3-plate mold, the Hot Runner mold, and the Insulated Runner mold. The Cold Runner 2-plate mold consists of 2 plates with the mold cavity and core mounted on them. The Cold Runner system molds the sprue, runners, and gate along with the parts. After ejection, the parts are separated and the rest reground. The Cold Runner 3-plate mold uses 3 plates to mold the part. These plates include the stripper plate, which contains the sprue, the middle or cavity plate, which holds the cavity, runner, and gate, and the movable plate, which holds the molded part. This type of Cold Runner mold design automatically separates the runner system from the part as the mold opens and is very easy to automate. The Hot Runner mold uses an electrically heated manifold that keeps the molten thermoplastic in the runners at the same temperature as the heating cylinder. The heated runner system is contained in a plate of its own and does not open during the molding cycle. Because of this, hot runner molds generate no runners or sprues. For this reason, hot runner molding, also known as runnerless molding, is fast and efficient. The insulated runner mold is much like the hot runner mold, but it uses a large diameter runner. During injection, the outer surface of the runner freezes. This insulates the center material, keeping it at the molding temperature.
I think that's it. Okay, there we go. There we go. Okay. So we're getting close to being out of time for the day, and tomorrow we can kind of start on this. But I do again, we kind of can think about that basic process in terms of injection molding. Also, we do like to, when we start talking about processes, look at equipment costs, tooling costs, some of the features of the process. And I always like looking at machines because you can get kind of an idea that these machines, the equipment costs for injection molding are relatively high compared to some of our other processes. Also, the tooling, if you notice, it looks kind of complex. You also do have a sprue, gate, runners in this process, so there is a little bit more of an opportunity for scrap. So we are going to tomorrow talk about injection molding, and we will probably also get to blow molding, thermoforming, and rotational molding, or at least start those as well. So I'm going to stop the recording and end class, although if there are any